Hello. So, um, so today I will explain applications of integrals. This is in chapter 6, and the first section of chapter 6 is the areas between curves. So I will explain the areas between curves. This section is divided into two cases. The first case is finding the area between two curves, where the area of the region bounded by two curves, where the top function is given as y equals f of x, the bottom function is y equals g of x, and that region is bounded to the left by the vertical line x equals a, and then to the right by the vertical line x equals b. So you have this region, this green region is what we call the region R, and we want to use integration to find the area of this region R. So over here, the region R is described as such. So the region R is bounded by the curve y equals f of x and y equals g of x. The assumption is that f of x is greater than or equals g of x. Basically, it means f of x is above the curve, and then g of x is the bottom curve. The vertical lines are x equals a and x equals b. So this is x equals a, x equals b. The assumption is that, of course, a is less than b with respect to the number line. So the question is to find the area of the region R. So to find the region, the answer to the question is this. To find the area of the region R, you'll have to integrate from a to b. You're going to integrate the difference of the function, the curves. So f of x is the top curve, and then the g of x is the bottom curve. So you're going to integrate from a to b f of x minus g of x dx. It gives you the area of the region that you're looking for. To simplify this a little bit, we put top, meaning top function, minus bottom function here, just to make it a little bit easier to understand. So here's the example. So you are asked to find the area of the region enclosed by the curves. So you give us y equals x and then y equals x squared. They didn't give us the boundaries, the limits of integration. So it's up to us to find those limits of integration. So first, it's good to know how to graph the region. How do you graph the region? Well, y equals x is this straight line that goes through 0, 0. And then y equals x squared is a parabola. And the two curves do enclose this region R. So this is the region R. And we want to find the area of this region. Now when you look at the region, the top function is this straight line, which is y equals x. The bottom curve is y equals x squared. So what you're going to integrate is top minus bottom. Top function is x, bottom function is x squared, so you're going to take x minus x squared. That's what you're going to integrate. So you're going to integrate x minus x squared. So this is top function, that's bottom function. Okay. Now, when you look at the problem, the limit of integration we're not given. So to find the limit, what are the limit of integration? The limit of integration will come from the points of intersection, of those two curves. You can see the two curves are they crossing each other here and here. So the x value of this point and the x value of that point are the one we're looking for to be the limits of integration. To get those limits of integration, you'll have to set the two functions to be equal, because the function have the same values at the intersections here, at the point of intersection. So you set one function is y equals x, another function is y equals x squared. So what you're going to do is set x to be equals to x squared to find the intersection. So it's being set here, x equals x squared. So this is a quadratic equation. Anytime you're trying to solve a quadratic equation, it's advised that you put everything, all the terms on one side and leave 0 on the other side. So what I did was subtracting x from both sides. So get this? Do not divide by x. Okay, you cannot divide by the variable. You're going to lose another 0. So what you're going to do from here is you're going to factor out x. When you factor out x from here, you get x times quantity x minus 1, and then you set x equals 0, and then x minus 1 equals 0. So you get x equals 0, and then x equals 1. So these are therefore your limits of integration. The smaller one is always called a, and then the bigger number is always called b. Okay, so you get a equals 0, b equals 1. So then you go back to your integration. So we are already here. So when you put the limit to be a 0 and then 1 here, then you're going to integrate x minus x squared dx. You find the antiderivative of x, which is x squared over 2. Find the antiderivative of x squared, which is x cubed over 3, and then evaluate at the 0 and 1. So you're going to plug in 1 for x first, always the top limit first. So evaluate this at x equals 1, which gives you this, minus, and then evaluate the same function at x equals 0, the bottom limit, which gives us 0. So when you subtract these two fractions, you get 1 over 6. So this is the area that we're looking for. Another example is that we are given these two curves, and we want to find the area of the region bounded by these two curves. Okay. So first we're going to graph the region. So when you graph this, you can use a calculator to graph this region. So it gives you, so this is y equals 12 minus x squared. And when you graph this, you get y equals x squared minus 6. And then the two curves do enclose this region here. So the question is, what is the area of this region? Again, here's a case where we don't have the limits of integration. So we'll have to find the limit of integration. So 1 is going to be here, the x values of this point, A, and the x values of this point, B. So we need to find them. To find it, we'll have to set the two equations, the two functions to be equal. So you're going to have x squared minus 6 equals 12 minus x squared, and then you solve for x. So again, it's a quadratic equation, so you will have to move everything on one side. What did I do? I did add x squared to both sides. So plus x squared, we eliminate this. Plus x squared is going to make x squared plus x squared to become 2x squared. Then I will add 6 to both sides. So plus 6, eliminate this minus 6, and then plus 6 to 12 is give us 18. And then to solve for x first, I'm going to get rid of 2, the coefficient of x squared. So divide both sides by 2. We'll get rid of 2 here, and then 18 divided by 2 is 9. Then when I have this quadratic equation, I will take the square root. I will take the square root of both sides. Remember, when you take the square root of the equation, you'll have to introduce plus and minus. So the square root of x squared gives us x, plus and minus square root of 9, which is 3. So this gives us plus and minus 3. So I have negative 3 and the 3. Negative 3 is less than 3, so A is negative 3, B is 3. So I go to integral. When you look at this graph, the top function is this one here. And this is the graph of y equals 12 minus x squared. The bottom function is this. So that's the graph of y equals x squared minus 6. Okay. So the integral is going to be top minus bottom. Okay. So it's going to be 12 minus x squared minus quantity x squared minus 6. So what I just said is this. So 12 minus x squared minus quantity. So I use parentheses here to make sure that this negative sign will be distributed to both x squared and minus 6. So when you distribute negative sign to x squared, you get minus x squared, and then negative and negative makes this plus 6. And then from here, you add like terms. So 12 plus 6 is 18, and then negative x squared minus x squared is negative 2x squared. So I will integrate this from negative 3 to 3. I find the antiderivative of 18, it gives us 18x. And then find the antiderivative of 2x squared, give us 2x cubed over 3. And then evaluate this at negative 3 and 3. So first, always plug in the top limit first. So plug in 3 for x, give us this. And then plug in negative 3 for x into this function, it gives us this. And then take the difference of the two numbers, and then you'll end up with the number 72 as the area that you're looking for. Okay, so so that's basically case 1, and then the next video is going to be on case 2. Thank you.